Welcome to Homework Lib.
This problem gives us another fun real world example that we can draw on. So we have a turbine that is malfunctioning and we are doing some diagnostics. So what we're doing to do diagnostics is turning on a voltage in the positive and in the negative and measuring the current. So whenever we turn on a voltage of plus 5 millivolts, we get a forward current IF of 0.407 milliamps. And conversely, whenever we turn on a reverse bias voltage of minus 5 millivolts, that results in a reverse current of minus 0.338 milliamps. And the problem wants us to calculate what the temperature and saturation current are for this junction. So, of course, what we're going to go to is our equation for the current in a diode, which has a saturation current in it, and it has a temperature, which are the two things that we want. However, right away, it seems like it might be a little complicated because we're solving this and there's an exponential. But at the end of the day, we have two unknowns that we're looking for, and we have two boundary conditions for which we can solve it for. Thus, um, in spirit of the hint, we're going to go our own way a little bit, but I like their idea to take x and let that be equal to e to the ev over kt, because our voltage, luckily, is about the same except for a minus sign. So if this is for when it's positive, then whenever the voltage is negative, there's just a minus in our exponential, which is the same thing as saying 1 over this term. Thus, it's equal to that, 1 over x, or x to the minus 1. And if we write out both of our equations here, we'll pick green to do this. I forward equals is times x minus 1, and I reverse equals is times x to the minus 1 minus 1. We have something that we can move forward with. So there's some algebra involved here. None of it is too difficult or anything like that. But I probably will skip a few steps just because it's a little tedious. But the first thing that we can do is solve for x. That's always a good idea, because if we solve for x here, we can plug it in over here. And to go about doing that, we should divide by is on both sides and then add that 1. So we get if over is plus 1 is equal to x. And then we can take that and put it in over here. And we'll go ahead and move this to the other side as well and add the same 1. So IR over IS plus 1 is equal to x to the minus 1. But we have an x over here. So let's send it on along to being 1 over IF over IS plus 1. But I recommend we multiply this on both sides. So we get a 1 over here and multiplied by this whole thing on the left side. And I can start a new page for that so we don't get cluttered here. And we end up with I R over IS plus 1 multiplied by IF over IS. And by this point, you probably see where it's all going. It's just algebra at this juncture. So you expand it out. IR, IF squared. Though just because it's simple doesn't mean there's no room for mistakes. You'd be surprised what factors and minuses you can leave off whenever you're doing a problem too quickly. So we can cancel these ones. And we can multiply IS. Well, okay, let's take it one step at a time. Cancel out the ones, and then let's move this term over here. Just subtract it. So we get IR, IF over IS squared is equal to minus IR plus IF over IS. So we can cancel one of these and move that up there and this down there to get that our saturation current is equal to minus IR IF over IR plus IF. All right, that is great. We have our relation for the saturation current. And then you need to plug that into our equations here. You can pick your poison. I say this one's probably a little bit easier. This part I'm going to just sort of skip through to the answer because it's really not too difficult. You get down to where your x is equal to minus IF over IR. And of course, we can't forget that we have replaced this x, so it's actually e to the EV over KT. Because at the end of the day, what we're really trying to solve for is temperature. And to get something out of the clutches of an exponential, you take the natural log on both sides. So you have EV over KT is equal to the natural log of minus IF over IR. And finally, you can figure your expression for T just as EV over K natural log IF over IR. And since we have everything, we have our voltage, these are constants, and we have these from what we've measured, just like we have all these. We can now calculate for this problem what our IS is, our saturation current, which is just 1.99 milliamps. It's so close to 2, I wonder if it's a simple rounding issue at this point. And then our temperature can be calculated as 312 Kelvin. So It just goes to show that even if it seems like you have a lot of unknowns, so long as the number of unknowns matches the number of equations or boundary conditions that you can put together, you will always be able to find a solution, even if it's a little tricky.